When a large language model answers a factual question, it isn't querying an external database. It generates the response from within its own internal structure. Many assume this knowledge lives in the attention mechanism, but attention is primarily designed to connect context between words in a prompt. It maps the relationships between terms rather than storing the facts themselves. The true storage vault is a massive section of the network called the multi-layer perceptron, or MLP. In models like GPT-3, these blocks house over 2/3 of the total parameters, providing the raw capacity needed to memorize the world. To find where a fact lives, we have to move past the idea of a searchable hard drive and look strictly at the mathematical architecture of the MLP. Consider a simple factual challenge, predicting the sport associated with Michael Jordan. The model must use its internal parameters in order to produce the concept of basketball entirely without any external help. Inside the MLP, the input words are represented as vectors, long lists of numbers, which flow into a massive grid of learned values. This grid is a matrix, and the core transformation happens through matrix multiplication. The input vector is multiplied against these learned numbers to evolve the data into a more complex meaning. Every fact the model knows is baked into the specific values of these matrices. Recalling a fact is the natural mathematical result of this transformation process. The rows within the matrix act as thousands of simultaneous probes, each asking a specific question of the vector. Is this a person? Is this a famous athlete? Is this Michael Jordan? When the vector aligns perfectly with the concept of Michael Jordan, the math triggers a nonlinear step called a ReLU. It clips away all the negative noise and allows a specific neuron to act like a logical AND gate, which fires when the identity is confirmed. That firing neuron then triggers a down projection matrix. This second step takes the identified concept and adds a new mathematical direction for basketball back into the original vector. These MLP blocks function as high-speed concept detectors, mathematically adding learned knowledge onto the context as it flows through the network. This process faces a significant hurdle. There are far more facts in the world than there are individual neurons in the model. Storing every fact on its own dedicated neuron is mathematically impossible at this scale. To bypass this, the network uses a geometric loophole called superposition, which allows it to pack many independent concepts into the exact same mathematical space. In our physical three-dimensional world, we are limited to only 3 truly independent perpendicular directions, the x, y, and z axes. But in the thousands of dimensions an AI uses, vectors can be nearly perpendicular. As long as you tolerate a tiny bit of noise, millions of vectors can sit in a narrow range around 90 degrees without interfering with one another. Because high-dimensional geometry allows these directions to safely overlap, the AI can store a nearly unlimited number of facts in the same internal location. This fascinating quirk of geometry, where entirely independent ideas can be securely crammed into almost perpendicular directions, is formalized by the Johnson-Lindenstrass lemma. It explains why increasing the number of dimensions in a model provides an exponential boost to its capacity for these superimposed ideas. These scaling laws are why larger models feel significantly smarter. By adding more dimensions, the model gains a massive nonlinear increase in the number of facts it can successfully overlap. Large language models hold human knowledge as a vast high-dimensional landscape where billions of facts exist in harmony through the sheer scale of geometry.